Okay, so thanks all for coming. This is now, I think, the fifth seminar in the New Directions in Cooperative AI series. And yeah, just many of you, I suppose, will already know this, so I'll just kind of quickly run through. But those who haven't been before, this is a new seminar series that we're running as the Cooperative AI Foundation. The idea essentially is to get people to kind of pose their own kind of research agendas and offer their kind of perspectives and visions for what research on cooperative AI could look like. What are the kind of main questions that need answering? What are the sorts of research and work that could answer those questions? You know, as a foundation, this is, you know, we're looking for this because, you know, that's what we want to be doing. We want to be supporting exactly this kind of research and answering exactly these kind of questions. So if you do have something that you think would fall into that category and you're interested in giving a seminar yourself, please do apply online. You can just find the application form via our website, and do feel free to contact me as well if you have any questions about what might or might not be suitable there. And of course, if you're interested in coming to future talks, in case you're not already on the mailing list, then please do subscribe to that. The second thing, just to really quickly flag, is that the foundation has also recently opened its first call for proposals. So in particular, we're looking to fund work that improves our ability to evaluate the kind of cooperation relevant features of AI systems. So this is kind of both theoretical work. So what actually is it that we're trying to measure here? What do we mean when we talk about kind of cooperation, which is quite like nebulous concept, and also more kind of practical things, looking at kind of benchmarks, stuff to do with code, etc., data sets, etc., for doing that. And again, all the details are online on the website, so I'll encourage you to have a look there. And again, please do get in touch if you have any questions about that. Okay, so I think that's everything I wanted to briefly say. So now I'll just introduce everyone. So today, our speaker is Dorsa Sadigh, who's an assistant professor in computer science and electrical engineering at Stanford University, and whose research is on the intersection of robotics, learning, and control theory. I'm sure we'll be hearing more about those in the presentation. And we are very fortunate as well to be joined by two discussants. So we have Hadfield-Menell, who is an assistant professor in AI and decision-making at CSAIL at MIT, and whose research is on the problem of agent alignment, so the challenge of identifying behaviors that are consistent with the goals of another actor or group of agents. And then we also have Robert Hawkins, who is a postdoc at the Princeton's Neuroscience Institute as a CV star fellow there, and his research is on the cognitive mechanisms that allow people to flexibly communicate, collaborate, and coordinate on social conventions in groups. Right. So with all that out of the way, I will stop sharing my screen and hand over to Dorsa. The floor is yours.
Okay, let me share my screen. All right, can everyone see this? Great.
Yeah, looks great.
Sounds good. So I'm not going to be able to look at the chat. If there's anything you want to ask during the talk, just speak up. All right. Yeah. So let's just get into it. This is going to be around 30 minutes, 35 minutes. So just a heads up on the length of the talk. And then after that, we can also of course, discuss these different directions. So I'm Dorsa, and my research is in general in the space of human robot and human AI interaction. I'm pretty interested in building algorithmic systems that can coordinate, collaborate, communicate, interact with humans. And today I want to talk about a slightly different topic. It's a practical topic. It's not that theoretical. And it's kind of like this topic of trying to understand what makes human data special. Because in practice, I've been working on this area for the past 5 years, let's say, and we make all sorts of assumptions about human data, even when we are trying to model humans in the best way possible. And that's pretty frustrating. So this talk is mostly questions and not too much answers or technical technical details of like what I've done. It's mostly like questions and things that I'm personally dealing with in my work, recently. But let's just start. Let's just motivate like why we care about this. So in general, as I said, I'm pretty interested in human robot, human AI interaction. As robots are leaving the factory floors, we're starting to see these types of systems interacting, coordinating with people. And one very common way of modeling this interaction that we use in human-robot interaction is this game theoretic type of modeling that I'm sure a lot of you guys are familiar with. So this is the most natural way of going about modeling interaction in these more practical systems. I have a human who has a model of the robot, maybe the robot's state, the robot actions, the robot's policy. And similarly, the robot is starting to build a model of the human. And there is kind of like this theory of mind or game theoretic perspective that goes on here. And this type of idea shows up in a variety of fields. It shows up in human-robot interaction. It shows up in reinforcement learning, in multi-agent reinforcement learning as opponent modeling. It shows up in NLP as like rational speech act or pragmatics. And in all of these fields, very quickly, people realize that this is computationally pretty difficult to deal with. So what we do is we approximate it and we just cut the game at some time step and do like an nth order theory of mind instead of like solving the full game. This is something that is, again, very common and something that we have also worked on, like as part of my PhD work at Berkeley. What I was looking at was looking at the interactions between autonomous cars and human-driven cars, taking this game theoretic perspective. And we were able to show very interesting behaviors. For example, when a car tries to change lanes, we were able to show that this car can take more interactive, assertive motion and basically nudge in front of other cars and make other cars slow down and influence them, which was kind of an interesting behavior you don't normally see from autonomous cars. But basically, this behavior comes out because we start thinking about the interaction a lot more carefully. And then about like a couple of years ago, we started thinking about this problem a little bit more, like this idea of theory of mind modeling. And we started looking at challenges like two people moving a table together, or maybe like two people playing a game of air hockey together. And one thing that we started noticing, like looking at human-human interaction, is that in a lot of these tasks, I really don't think people are doing theory of mind modeling. Like when two people are moving a table together, I really don't think that is what is happening in people's head, trying to like build some sort of high dimensional belief structure, like doing recursive belief modeling. And then it is really difficult for two robots to do these types of coordination tasks, like a decentralized robots without communication to do these types of coordination tasks. But again, humans seamlessly do this. So we started thinking about this problem, again, in the setting of air hockey. And we thought about, okay, like what is it that the human does? So if this human is my opponent, well, this human is going to have an action space that lies in the 7-degree freedom space, because the human and any fancy robot arm has 7 degrees of freedom. So the actions like really lie in R7. And if I want to like do this from perspective of a robot, I need to build a belief over that. And based on that, I need to try to coordinate and do partner modeling. But I'd argue that, again, as humans, that's not what we do. And that's not what we do. What we do is we live in a much lower dimensional space. For example, we might just look at the direction of the puck. Like that might be the only thing we pay attention to. And then based on a model of direction of the puck, like we are going to like have a model of the partner. And that is oftentimes sufficient for doing this type of task. So I would argue that in a lot of coordination tasks, there is this sufficient statistics that exists that is sufficient for coordination, for interaction. And what I'm proposing here is maybe we should try to go and learn what that is. Maybe we should try to come up with an approximation of that low dimensional representation. So the idea is not that there are a set of intents and we want to do belief modeling over intents. Of course, there's quite a bit of work that does belief modeling over intents. What I'm arguing is I'm not even sure what is it that we are calling intent. Could we directly identify like what is that space of intents or goals or conventions? So what we want to do is we want to basically figure out what these low dimensional representations are and coordinate based on that, and even like use those for adaptation, because potentially when we think about the person changing over time, those low dimensional representations are the things that are changing over time. So we took this idea and we actually like demonstrated that we could do partner modeling in a much more like data efficient way by capturing these low dimensional representations. And we had this algorithm called Lily, learning and influencing latent intent, which after 4 hours of training, it was able to coordinate with this other arm. And not only coordinate, it was even able to influence the other agent to act in ways that are useful for it. And it had like success rate of 90%. So compared to, let's say 30% or 40%, which is the success rate of like state-of-the-art reinforcement learning, like soft actor critic. All right, so that's all great. So what did we do here? We looked at human-human interaction. We thought humans are coming up with these low-dimensional representations, and we were really motivated by that. And based on that, we tried to build this interactive system that was a lot more effective, data efficient in partner modeling. But I kind of like motivated all of this for interactions with actual humans. And I didn't show anything working with actual humans. Like the video that I just showed you was two robots coordinating with each other. And you might say, well, did you try this with an actual human? And well, we did. So here is Dylan Losey. And Dylan was an author on this paper. And what Dylan is doing is trying to play with this robot. And the strategy that Dylan is following is the exact same strategy as that other partner robot that I was showing 2 slides ago. So Dylan is really trying to be exactly like that robot. And even in this case, where in terms of like decision-making, Dylan is exactly doing what the robot has already seen with the other robot. Dylan is trying to be as robot-like as possible. Even under that, the success rate drops to like 70%. And part of the reason is that the human data is very variable. Like even again, like decision-making is the same as what the robot was doing, but like the slight like differences in friction and pushes that Dylan is putting in, like puts the data out of distribution for the robot, and we start seeing more failures. Which like I found really interesting. And this is not something that we have only done. There's work from Anka Dragan's lab from Berkeley, where they showed that you can train these self-play agents in the game of Overcooked, and the self-play agents are not going to be able to coordinate with humans, which is kind of clear, right? Like if I pair up 2 RL agents, there's no reason for them to build the same sort of conventions with humans. And in general, even if I make my humans to follow the same sort of conventions, there is still quite a bit of variability in the human data that makes things just not work as we expect. So in a lot of our work, we tend to model human decision-making as how the best robot decision maker would act. And then we run user studies, right? We want to show human-robot, human-AI interaction, but then we ask our humans to be as robot-like as possible, which I find kind of silly, like the fact that we do that. And this is something that we do all the time. Like I showed like in a video of Dylan like playing this game. So you might be asking, well, why are we not going and directly learning a model of the human? Like how difficult could that be? Like why is it that we are not learning directly? Like what is it that humans are doing? And then that's a good idea. We should be doing that. We should be doing that more. But that is very difficult. And that is why I feel like a lot of times researchers in this area like shy away from it. Here's an example of why that is difficult. So about, again, a couple of years ago, we started looking at this problem of assistive feeding. It's a very interesting robotics problem. You got to pick up food. You got to like worry about deformable objects. But it's also a very interesting interaction problem. It is really like thinking about the human and robot interacting with each other, right? Like robot bringing food to a person's mouth and transferring that, which is kind of like a very interesting and safety critical interaction problem. And here what I'm showing is a hand-coded policy. It is a model-based policy that has a model of the person's face, where the person is like sitting. And then based on that, it is trying to basically transfer the food to a person's mouth. So we got this policy. And like, as you can see, the model is a little bit off. So the person needs to like back up. And it's like incredibly uncomfortable. Like even like watching this video is uncomfortable for me. So it's pretty difficult to do this type of task, even when we have models of humans. And you might say, okay, like we should maybe do a little bit more learning. Like, why aren't we throwing machine learning at this? Like machine learning has solved everything, right? Maybe it will solve this problem too. Well, not really, right? So we could try to use reinforcement learning here. That's not necessarily a good idea because I don't want the food to hit the person's face and get a negative reward. That sounds pretty dangerous. I don't have good simulators here. I don't have a good simulator of a person's mouth or the food or any of that. So I can't really generate data. So reinforcement learning is like out of the picture. I can't really like go there. I could try to do imitation learning. I could try to collect expert demonstrations, and based on those expert demonstrations, like figure out how a human would do this interaction and how the human would transfer the food. I think that could be a good idea. But in general, we need lots of data for that to actually work. We try to collect data, and like the policy that we are getting from imitation learning is far from what we want in this setting. So that makes things pretty difficult. And at this point, we were thinking, okay, how is it that we learn how to eat as a child? Like me as a person, like how do I learn how to eat as a child? And you're right, like expert demonstrations is definitely one of the sources. We all probably had someone like a parent or an adult who like taught us how to pick up food and bring the food to our mouth. But I would also like to argue that even we as humans, we went beyond expert demonstrations. There are many other sources of data that we should really tap into and leverage. And in practice, again, as humans, we do that all the time. For example, when it comes to feeding ourselves, like a lot of times we look at unstructured play, like the fact that we play with our food gives us quite a bit of information about the state space, about the dynamics of the food, which is like not replaceable by expert demonstrations. Or we might even look at suboptimal agents, right? Like there's a lot more data of that. Like we might look at our siblings or our friends who are also trying to eat and maybe they're not so great at it. But based on that information, we can actually like try to learn a better policy for picking up food. Or we might think of comparisons, right? Like there might be like a better bite of food versus a slippery one, and we start making these comparisons. And all of these different sources of data together are the things that are teaching us the policy of picking up food. So similarly, I think in robotics, we should be doing the same thing, right? Like, or in the human AI interaction, human robot interaction, we should be really doing the same thing. If we want to have a better model of the person, we should try to tap into many different sources of data that is present and try to learn from all of them. And that is something that in general, like we are looking at in my lab and in a lot of other labs in general, we are interested in this idea of learning and really tapping into other sources of data. So just to create a laundry list of these, I'm not going to go into any of them really in detail, but we can talk about that during discussion. Just to create a laundry list of like, what are these other sources of data? Unstructured play is definitely one of them. So like collecting these types of play data of an agent, maybe teleoperating a robot and moving objects around, or synthetically generated play data. Suboptimal demonstrations, again, like we have a lot of that, like maybe people are not good at doing various types of tasks. So maybe we could have suboptimal ways of like achieving tasks, and that still like gives us quite a bit of information. Comparisons is definitely an interesting source of data that we have looked at very closely. So how do we look at pairwise comparisons or rankings? And for example, like in this case, the robot is providing 2 different walking gaits to these people, and one might be more comfortable than the other. And these types of pairwise comparisons are going to give us quite a bit of information about the AI agents or robots policy. If we actually have a robot, then that has a physical embodiment. So we could move the robot. The fact that we can provide physical corrections is quite informative in this domain. And then finally, like I think 2 other data sets that people are really excited about these days are things of the form of human videos or language data sets. So because, and part of the reason is we have large offline human videos and language data sets. And it would be pretty interesting to try to really tap into these types of videos, like videos of people doing various types of tasks on YouTube. Like if a person is cooking on YouTube, like in a YouTube video, could we really like tap into that and learn something useful? And I think that area is pretty interesting. So I understand a lot of things that I'm putting here maybe is not immediately, like it's not about like a coordination or cooperation problem. It is really about learning a better policy, but it is about learning a better interactive policy from human data. Because like a lot of data sets that we have are human data. That is really the thing that we want to tap into, because that is really the thing that has a true reward function that we would like the robot to follow. Like humans like are better at like doing these types of tasks as opposed to me trying to write down the reward function. So I think in general, we should try to tap into these types of data sets, not just for the sake of cooperation, but also for the sake of robot learning. But robot learning and having robot policies are a prereq for cooperation. So I kind of think like this is really necessary. So that kind of brings me to this idea of learning from humans. I think we got to tap into these types of data sets to try to learn from humans. And as I mentioned, I'm not going to go into detail into any of these directions. I can talk about them offline, but in the next like 1 minute, I'm going to just briefly talk about 2 minutes. I'm going to maybe briefly talk about how we can tap into unstructured play data, because I think it is a very interesting source of data and people don't work on it enough. So I want to talk a little bit about this idea of learning from play and a recent work that we have been doing in this space. So what is play data? So human play is unstructured, undirected multitask demonstrations. So I might have, again, a person teleoperating this robot, moving this object around, bringing it up a platform, lifting it, putting it down, pushing it, these types of various behaviors in a very long sequence. And the reason play data is really useful is that it is incredibly cheap to collect. If I were to collect imitation data, I needed to have exact task specifications, and I needed to reset the environment and then do that same task again. And that is pretty difficult, even if it is a human providing that data. If it is a synthetic agent, like an RL agent providing that data, it's even more difficult because you really need to have really good task specifications to be able to collect that type of data. And on a real robotics agent, resetting is difficult, right? Like, how do you reset the environment? But if you're collecting play data, again, it's this long sequence that doesn't care like what the task is. And that can potentially address the scalability issue that we have, like, again, in these types of domains. And similarly, if you're collecting play data, we're going to have quite a bit of broad state action goal coverage. And having the state action goal coverage can actually address the generalizability problem that we often have when we are trying to do multitask learning. Because we are not only going to see the initial state and the goal state of a single demonstration, we are actually going to see quite a bit of, like, have quite a bit of a state action coverage of all of the environment. And that can provide more generalizable, robust policies. And then finally, like, this allows us to have access to human priors on goals and behaviors. And that is really something that we would like to get at. So, okay, how can we learn from play data? So our insight here is that we can really view play data as a sequence of object interactions. So play is really this long sequence of back-to-back interactions with the environment. Like, if you pick any segment of play data, it probably has some pre-interaction phase where the robot is going towards the object. And then there's an interaction phase where the robot is making contact with the object and influencing the object, pushing the object in this case. And then there's a post-interaction phase, maybe where the robot like retrieves and goes away from the object. And this post-interaction phase is really the pre-interaction for the next interaction that will come up. So the key idea here is, if we think of play data as object interactions, this can provide a better and smarter way of segmenting the play data set. And then we can really like learn from that play data set. So the way we are learning from the play data set at a high level, again, not going into details here, is that we are sampling an object goal state from the post-interaction phase. And we are taking this interaction phase where the contact with the object is happening. When we are actually having that object interaction, we're trying to encode that particular phase into a low dimensional representation Z. And this Z is capturing the plan. It's really capturing the affordances, like the fact that the object is being pushed. And then what we're doing is we're learning a policy that is conditioned on this low dimensional latent plan or affordance, as well as the goal. So in test time, then I can call this policy based on the Z's that I've learned in training time on a new goal. And I can do various types of tasks in test time based on this policy. So that was kind of like a very quick overview of this algorithm called Plato, predicting latent affordances through object-centric play. So let's see how this works in practice. So we looked at a number of primitives. These are seemingly easy primitives, like pushing or pulling or lifting, tipping. Side rotate is pretty interesting. You got to go to the side of the object and flip it. And the reason I'm saying that they're seemingly easy is that actually some of them are not very easy. Side rotate is a pretty difficult task, and it does have similarities to tasks like turning a doorknob. So it is actually like pretty difficult. And you also like vary a number of parameters like block size, masses, positions, and so on. So we have these number of primitives. And what we decided to do is we decided to kind of compare like what this algorithm Plato does in comparison to other types of techniques like play using goal condition behavior cloning on play data, and play LMP, which is kind of like prior state of the art in this area that doesn't have this view of this object-centric view that I was talking about. And we basically see like performance increases across all these different domains, especially like in more complex like tasks like side rotate, you start seeing quite a bit of like increase in performance. So that's all great, but what I'm showing in this table is unsynthetically generated play data. So the play data here is 7 hours of play data. It's 7 hours of synthetically generated pushes and pulls and side rotates and tips and things of those forms. And we thought, okay, how difficult would it be for me to collect actual human play data, 7 hours of actual human play data, and then based on that, run the same algorithm? Like, it should work, right? If I have the same amount of data in this very simple 2D environment on actual human data, like that should, like to our knowledge, that should have worked. So we collected play data at the surface, like looking at their trajectories of the play data that we have from humans, it looked exactly the same as the synthetically generated data. And then nothing worked. None of the algorithms worked with actual human data. which again, like I found really interesting. So why is it that like human data is giving us so much trouble? So what ended up happening was we increased our data set of human data. We changed our architecture. We made it larger, more expressive, changed hyperparameters. And then based on that, we started seeing some reasonable results, but it is still not as good as the synthetically generated data. Again, if I visualize these, they look exactly the same. So what is happening is I'd argue that human data is a lot more variable, and it has a lot more interesting like biases and suboptimal things that we tend to call suboptimalities that like synthetic data just doesn't have. And like when we start making these algorithms like all over in robot learning and AI, and we say, oh, it's going to work with actual humans, it doesn't until like we try it and we realize it actually doesn't. So I think we should do a really like better job when we are trying to coordinate like with actual humans and try to figure out how to deal with human data. And so far, most of the work, what it does is it tries to learn interactive robot policies, potentially from many different sources of data, because that would be nice. But then people usually like treat humans and robot data kind of similarly from the perspective of the robot. And in practice, they are pretty different. So here's an example of like how they're different. For example, you can look at push primitives in this 3D environment. 3D environment is easier to like visualize and start seeing the differences. So the scripted push demonstrations are, again, a lot cleaner, even though like we add noise and we try to do data augmentation. And the human play data, again, a lot more variable. It does have things like pauses in it that we don't normally see in robot data. And most prior work that actually use human data, what do? They take human data, they remove the pauses, they do a ton of post-processing to make the human data, again, as robot-like as possible. And then after that, like we run our algorithms based on that, which again, like I find interesting that we don't talk about like these types of post-processing that we do on human data. So what should we do? How can we do things better? So again, like this talk is more about problems rather than solutions, but in terms of solutions, I think there are potentially like two different ways of going about this. One is the data approach, right? So I have this human data, it is more variable, it has inductive biases, it is more suboptimal. Could we identify what that is? Could we identify like why the human data is different from robot data? And could we potentially come up with better data augmentation approaches that could potentially like be helpful in these settings? I think that would be an interesting research direction that again is not as well studied right now. The second approach is maybe an algorithmic approach, right? Like maybe we can come up with better algorithms here, and these better algorithms can help us. And the reason I think this is an interesting approach is that, again, in these types of works, like what we tend to do is we tend to take an existing machine learning algorithm with the assumptions of those machine learning algorithms that already exist, and we try to apply it in these settings. And that doesn't really work because the existing machine learning algorithm makes assumptions like the data is IID, and nothing about our data is IID, right? And that's just one example of the type of assumptions that is present in most of ML algorithms, and it's just not true in practice. So I think we should start thinking about, okay, what are these specific behaviors? What are these specific characteristics that, again, is present in our data, and how that should affect our algorithms, how that should change our algorithms. One example of that is there was this paper, RoboMimic, that came at Coral 21. This was from Stanford Vision Lab. And it was an interesting paper. So they collected a nice data set. So the data set is data from 6 humans. So these are 2 worse humans, 2 okay humans, and 2 better humans for various types of tasks, like putting a ring on a peg. And in this paper, like what they did was they compared the number of imitation learning policies, like behavior cloning, with a number of offline learning, offline reinforcement learning algorithms, like Iris here as an example. And they showed that actually in a lot of these types of tasks, behavioral cloning, if you treat it right, if you do behavioral cloning right, meaning that you would use RNN, like an RNN like layer on top of things, that could potentially like outperform like fancy offline RL algorithms, which again, I think is a pretty interesting result. Like previously, like people were doing like all these different types of offline RL algorithms, not even realizing that, or I think they would, but maybe they realized it. But I think in general, it's pretty interesting that simple behavioral cloning, like using RNN on top of it, right, like is actually going to outperform like these algorithmic advances that we start adding in. So we should, and why is that? Because of course the data has history, right? Like of course this is like trajectories that is not Markovian, right? So I think we should start like thinking about these assumptions that we make, and we should start building algorithms that really leverage like what is present in our data. Kind of like building on top of this work, like we have a recent work where we are trying to like tap into another suboptimality that is present in the data, which is the fact that, well, we have demonstrations from a mixture of demonstrators like suboptimal humans. And our algorithm, iLead, what it is doing is it's trying to estimate both expertise and the policy at the same time. And the idea is, okay, if I know my data is coming from suboptimal humans, maybe I should try to identify like the level of suboptimality and expertise and really learn based on that. And like our algorithm iLead outperforms like Iris and BCRNN in a number of these tasks. And kind of the interesting thing of this algorithm is that we are estimating expertise and policy even without having any access to any reward signal. So it's kind of doing it in an unsupervised way. Again, not going to details of this, but happy to chat about it during the discussion phase, like if you want to talk about this algorithm and what it is doing in more detail. All right, so what have I talked about so far? So I've talked about this idea that we got to learn from humans, because if we don't, we're going to come up with these algorithms that actually don't work with humans when we start thinking about cooperation. And one way of learning from humans is the fact that we can tap into many different sources of data. We can really leverage play. We can leverage suboptimal demonstrations. Maybe we can leverage offline data sets like videos. And then in addition to that, human data has a lot of variability, suboptimality, biases. And I think we should start thinking about how we can augment our data sets to capture these variabilities instead of just filtering them out. And in addition, maybe we should come up with better algorithms that can express and learn from variable human data, that can actually do a better job with the fact that human data is variable. All right, so that was kind of a big chunk of my talk, but like in the last like 5 minutes or so, what I want to do is I want to take a different perspective to the problem, which is this question of, can we teach humans, right? So far, we've been basically treating these humans as agents who are maybe suboptimal or are doing something that is different. And we have talked about better data, better algorithms to use that human data. But we have treated humans as these fixed agents, as like agents that are providing data to us. But in practice, if this human is suboptimal, maybe we can teach them to not be suboptimal. Like if this human is providing this data that has a lot of pauses and uncertainties in it, maybe we can kind of help them realize that, or maybe help them like better teleoperate a robot. And I think this idea of teaching humans in general is a pretty interesting idea. It has been around for a number of years in various fields in cognitive science, in machine learning, in education. AI and education has been thinking about this quite a bit. And I think it is still like there are still a lot of open questions there. So one particular, like I think, direction that we need to really think about carefully is to start with, like, why are humans bad at some tasks? Like why are they suboptimal? Like, I feel like we tend to, again, like bucket humans into, oh, they're suboptimal, but we don't really like talk about why they are suboptimal. Like the reason a person is bad at maybe solving a math equation could be pretty different from why they're bad at chess versus why they're bad at riding a bike or playing piano or flipping a pancake or maybe finding their keys in their bag. So these are very different types of tasks. I understand some of them are decision-making tasks, some of them are motor control tasks. So we can have like that division. But even beyond that division, right? Like people are bad at these types of tasks because maybe they have bounded memory. They can't really capture the full like tree of playing chess in their head. Or maybe they have bounded time, like they have to quickly decide like what the next action should be when they're riding a bike. Or maybe they have bounded attention. They can't pay attention to everything at the same time, or they have partial observability. And there are very different reasons for why people are suboptimal when it comes to doing various types of tasks. And without identifying that, I think it becomes really difficult to model humans. It becomes really difficult to teach humans. It becomes really difficult to actually leverage the data that is coming from humans. So there was this work from Berkeley that was trying to like get at like some of these issues. So this is a work from Anka's lab where they were looking at landing a lunar lander, and they were looking at human inductive biases about dynamics. So the key insight here was that if people are using their keyboard to control a lunar lander, they think they are doing position control. They think when they are pushing on right on the keyboard, the lunar lander should go to the right. But in practice, right, in practice, they're controlling acceleration. And people are bad at understanding dynamics and acceleration. So that's why they don't have a good estimate of how to control the lunar lander and land it, which I think is a very interesting work. I agree with the premise of this work. But if you get a person to play lunar lander, right, like for, I don't know, 10 minutes, they'll learn how to do it. They'll learn like that true dynamics. And I think it is interesting to think about that adaptation, right? How is it that people are losing those inductive biases and adapting? Like, could we model that adaptation in the human data? So kind of on the topic of what does it take to teach people to be less suboptimal, I think there are two key components. One is we need to really identify why they are bad at task, why they are suboptimal, and then really study how they can get better. And again, most of prior work in this domain, in the space of education, it is really about a very specific type of task, like solving math equations. Like the tutoring systems that are out there, things of the form of deep knowledge tracing or knowledge graphs, they're really about very specific decision-making tasks. And I don't think they apply to, let's say, landing a lunar lander. And then similarly, once we have that, I think we should start thinking about teaching. Only then, once we have this model of the person, we can start thinking about teaching and how we can teach the person to become better. And on the topic of teaching, I think there are a lot of interesting questions there too. Can we do skill discovery? Could we identify what are the skills that we got to teach a person? Could we generate a curriculum or drill to teach a person? And could we do personalization? So ideally, I would want to have a system that kind of acts like a parent or maybe training wheels of a bicycle, and basically identifies like what are the best ways of keeping the human, in this case, the child, keeping them safe, but also like teaching them these different types of skills based on the model that you're building of the person's learning. So again, on this topic of how to teach humans, so what I've talked about so far is pretty high level. I haven't really talked about anything like technical, but I think there are a lot of open questions here in terms of identifying human suboptimalities and really tracing their knowledge, how their knowledge is adapting. And then once we have that, on the topic of teaching, I think we should think about skill discovery, generating curriculums, drills, and personalization. And all of these questions are pretty exciting, I think, in the space of human AI, human robot interaction. And finally, in the last like 2 minutes, let me also try to close this loop. So there is kind of this idea that, well, the human was suboptimal. Maybe we should teach them to not be suboptimal. And maybe we can close the loop of theory of mind here. And one other thing that we can do is maybe we can teach the human to be mindful of the robot being suboptimal, to be mindful of the robot's learning process and the learning model. And for that, I want to just very briefly mention one work that we are looking at and dealing with, which is kind of like the space of the works in the space of like shared autonomy. So there was this paper at Coral this year, which was basically a paper around shared autonomy, where again, like we have the usual task of picking up a ring and putting it on a peg. And basically the robot might try to do this, but the robot might identify some novel scenarios or some risky scenarios. And in those scenarios, it's going to query a person and ask a person to come and take over control and provide human data. And it's a wonderful work because it takes human data and it basically demonstrates that you can have this cooperation between the human and robot. And based on the human data that you're getting, you're going to have a better system at the end of the day. Wonderful. So we took this work and we tried to reproduce this work. And Ryan here is the first author of this work. Ryan did a great job like putting out the code out and putting out his data. And it like works wonderfully on Ryan's data. And then Madeline and Sid were students in my lab. So Madeline and Sid tried to provide data, and it turned out that things didn't work as greatly with Madeline and Sid's data. And we were pretty confused about this for the longest. So let me tell you that success rate here, the kind of nominal success rate of the model, again, a model trained on Ryan's data, is at 20%. So if I give more Ryan's data, then success rate is going to go higher. But what ends up happening is if I give some Madeline's data, it's actually not, it's changing, maybe it is improving, but it's not improving as much as like Ryan's data. And then when Sid is providing data, like it's actually hurting the system. So Sid was giving data and performance was going down. And we were like really shocked, like why is it that performance is going down with Sid's data? And again, when you're visualizing these things, it looks great. Like what is happening here? So here's actually, let me show you a visualization of Ryan's demonstrations and Sid's demonstrations. They seem fine to me. Both of them are doing the task, dropping the object, like very clean demonstrations. Again, very robot-like clean demonstrations. So what is happening here? So we decided to plot the likelihood of these data that's coming from these different people, likelihood of compute the likelihood with respect to the nominal data set, which was Ryan's data set. And of course, Ryan's data has higher likelihood because it's coming from the same data set. Madeline's data is kind of in the middle. And Sid's data has very low likelihood that's coming from that it is coming from Ryan's demonstrations. And the reason is something very simple that maybe it is like too quick to like watch in the video. What is happening is like when you rotate the gripper, the order of rotating the gripper once you pick up the ring versus once you're placing it, that order is flipped in Ryan's data versus Sid's data. And that is the thing that puts Sid's data out of distribution for Ryan. And because it is out of distribution, then our model is actually going to have a hard time, like even leveraging like Sid's data. Sid's data is hurting our model. So I think this is, again, a very interesting phenomenon. Like how are we collecting our data? We are just very careful. We make sure that it's coming from the same distribution, it's coming from the same author, it's coming from the same person. And then we claim, I mean, not we, but in general, like at the end of the day, we assume that this is going to work with all sorts of humans, and it doesn't. So I think we should really like think about how to leverage human data a lot more effectively. And I think this has quite a bit of relations to topics around transparency and topics around legibility, really. So like this idea of having legible motion is work from Anka Dragan's thesis, which was basically this idea that the robot should be maybe more legible, more predictable, more transparent when it is operating in the world, because that helps the person to know what the robot is trying to do. And I think in general, like in these cooperation type of tasks, the robot should be more legible about how it is learning, especially if it's a learning agent. It should potentially like be transparent about how it is learning, and maybe even guides the person. Maybe we can guide Sid to provide in distribution data. So with that, I'm just gonna close it here. Just to summarize, I talked about learning from humans. You can tap into different sources of data. You can augment data sets. You can come up with better algorithms. And I think we should also think about teaching humans, because yeah, humans can adapt. And for that, we should think about suboptimality of humans, tracing their knowledge, come up with better ways of teaching, and maybe be more transparent when it comes to guiding the human to provide us better data. All right, I'm gonna stop here. Let me maybe stop sharing.
Okay, great, fantastic. Thank you, Dorsa. So I think probably I'll pass over to Dylan and then to Robert if they want to offer their thoughts. And then yeah, if you afterwards kind of want to come back to those, and then I guess that'll probably open up all sorts of different kind of things. And we've already got some questions in the chat, so we'll move on from there as well, if that suits you.
Great. So thank you so much. And first off, let me say, Dorsa, I'm always impressed by your slide design. That was beautiful. So let me get my screen shared, and I will share a couple of thoughts. I'm sorry I wasn't able to get the funny GIF in at the last minute. It just came to me, but we'll see how I can do. Okay, so sharing screen. Here are some thoughts that I had on what makes human data special, which is a presentation by Dorsa. Thank you again. So first off, I think I wanted to start talking about some of the examples you raised. I mean, a lot of this was about how learning from human data is really challenging. And I wanted to raise the point that I think is sort of sitting underneath a lot of that, which is that it sort of looks like this is challenging, especially on cooperative tasks. Like there's some sense in which we can get away from using human data in competition, and we can build robust, like AlphaGo and those classes of things didn't have to rely on collecting tons of data. In fact, they went from using data to not using data. And I think this raises a really important question for this group in particular of, does this mean that cooperation with humans or cooperation across different agent types is perhaps harder than competition between agent types? And to refine that a little bit more, I think you might ask the question, when is cooperation harder than competition? And so that's something that I think might be interesting for us to discuss in the Q&A session and afterwards. I think, to me, this is a theme that's been coming up a couple of times in different pieces of work, and it feels spot on for this talk and this group. And to add on to this a little bit more, what factors actually make a cooperation task harder than a competition task? And I think that's a fascinating question that this raises.
Should we talk about that, or should we? Oh, do you want to? Okay, go ahead. Yeah.
I think you'll have a bit of time afterwards for a response to my response. unless I'm
you're
wrong.
right.
But
Yeah,
in any case,
you're absolutely right.
yes. So, but I think that will be a great thing to discuss. The next thing I wanted to talk about was observing suboptimal agents, which I think is a really interesting source of data that you didn't talk about quite as much. So as a good academic, I will use this to point out that there are actually some examples we have where learning from suboptimal agents can be more efficient than learning from optimal agents. And so this is a figure from my paper in 2016 on cooperative IRL, where we're showing the results of inference on demonstration data. And you have ground truth data. So this is a reward function sitting underneath where you've got a grid. And I think the white peaks are high reward and the black is sort of low reward. And if you do an expert demonstration, you just start somewhere in the middle, go to one of the peaks and stay there. And I was looking at things like instructive demonstration, where we were saying, you can actually give demonstrations that lead to better reward inferences than the ground truth. But what was really interesting here is this built around a model where you said the probability of a trajectory is related to e to the lambda reward of that trajectory. And if you look at the performance of the best response of the robot doing inference, so you look at a plot here where regret, so you want this to be lower, is on the y-axis, and lambda here is like how optimal does the robot expect its data to be, you actually see that regret is minimized for a value of lambda that isn't the person being as optimal as possible. So I think this points to a lot of interesting directions to explore for leveraging suboptimal data for learning as a way to do better. And then I wanted to, I think this is probably one of the last points that I have here, but I wanted to talk about the ideas around learning from play, because I think it's a very interesting direction to explore. But one of the things that it seems to rely on is a notion of where goals come from or what types of goals are present. And I wanted to make a hypothesis here that part of what allows learning from play and these types of methods to do well is, at least in these types of physical game environments, we actually already have a shared abstraction between the person and the robot, which is effectively these object level abstractions of like, my goals are to move objects around. It's not to wiggle my arm in a really wonky way or something like that. And so this, I think, brings up a question for cooperation research, which is, should we be investing time into teaching and learning shared abstractions between the person and the robot? And I'm sorry for false advertising, because I just realized I had one other point that I added in here, which is, first off, this is where the GIF was going to go. I think this is a pretty savage way to put your students on blast like this, Dorsa. So I just wanted to point that out. Poor Sid. Sid is great. Anyways, so the question I wanted to finish with is cooperative data collected or produced? I think there's this analogy we have in machine learning of like, data is the new oil or whatever, where you go around, you collect a bunch of data and then you learn about the world and that's it. And I think maybe one of the features of data where you're learning to assist someone or data in a cooperative setting more generally is that you have this, data is generated by some goals, but it's also generated by what is the system going to do with that goal. And I think this is an incentive misalignment in a lot of ways between general data that you might collect and teaching data from a system. And I think this is an interesting direction to explore, right? Like a parent doesn't just happen to teach their child how to eat spaghetti. They're very invested in that child learning to eat spaghetti and not get it all over the floor, and staying alive and all of those other important things. So I think that's the last point that I would raise here. And with that, I think I'm probably about at time. So I will hand it over to Robert.
That's great. That is perfect. Thanks. I'll just ask Dorsa to hold off on responding to questions, because I know the temptation is there to just, after the first slide, even just to dive straight in. But I feel like if we do that, then we'll never hear Robert. So I'll hand over to Robert first, and then we'll get stuck in.
Fantastic. Yeah, I didn't prepare slides. I wanted to give more kind of informal, but still kind of structured remarks, I guess. So I feel like I play this role of being kind of like the cognitive science person in more like AI settings and more of the AI person in cognitive science settings. So in this place, I'm putting on my kind of like human psychologist hats and kind of thinking about, you know, basically this entire field that is about like creating benchmarks for people, right? Which is also known as psychology. And I think that we've learned a lot of interesting things from this that I think characterizes like some of the things that make human data different. And I think kind of go into these cases of like, why does it break when you use human data, even though you're giving humans exactly the same task? And I think one thing that's kind of interesting that cognitive scientists have learned to kind of deal with in various ways is like modeling many sources of variability explicitly. So there's like this really deep insight going back to the 1930s by Bartlett that humans are like general purpose machines. So just because you put them in a particular task doesn't mean that you can get them to shut off everything else they do, right? So basically you can't like force people to restrict their cognition to the thing you're asking them to do. They're taking their kind of general purpose thing and then like directing it toward this specific thing, which basically means that like there's a lot of task irrelevant stuff going on in human data. And there was actually a really interesting demonstration of this too in a mouse like neuroscience study, where for a long time there were all these concerns about like why decision making was so noisy and unrelated to certain brain signals. And then they started measuring all these other little things the mice were doing, like scratching themselves and I don't know, like, you know, stretching and I don't know, like, and then it turns out that that accounts for like 90% of the variance in the data or something. So this is Anne Churchland. It's a really cool study. And I think that there's similar things going on with humans where like a lot of things people are doing in these tasks are kind of task irrelevant, right? Like they might like be shifting, you know, like moving their thing, but then like they need to like itch their head and then go back to it or whatever. You know, there's like a lot of kind of idiosyncrasy in human behavior. And I think that maybe my one pitch that I'm kind of excited about recently is this kind of like structured modeling of sources of variation, which is kind of like personalization. And so it's kind of on line with the adaptation personalization theme, but it's a certain way that cognitive science, so there's a particular class of models called mixed effects models that are tremendously popular in the social sciences, where there are various things that you know are sources of variance, right? That are kind of like irrelevant to your task. Like there may be just like differences in like person A versus person B. There may be differences in like one particular like interface versus another interface. There may be, you know, there's all these kind of little tiny like metadata kinds of things. And you want to like build those into your model to kind of like kind of partition them out, so that the thing your model is learning is the stuff that they all share in common. And actually, when you look at it from that perspective, having this kind of variability actually gives you more robust models as long as you are deliberately accounting for it. So I think that that's kind of like, and we have some work coming out soon that is kind of trying to extend this kind of mixed effects framework into, for example, language modeling or like conditioning policies. And I think that this is kind of an exciting direction.
Cool. All right. Is it my turn now? Okay.
Yeah.
All right, cool. So I was trying to take notes so I don't forget things, but like I might forget things in the middle. So so there are 4 things that I want to like talk about, right? So one is, so let's start with the first point that Dylan brought up, which is competition versus cooperation. And I think maybe there was a question I'll get to that question later, the question on chat. But yeah, so I do think I agree with that. I do think that we see a lot of these types of issues in cooperation more than competition. And I think part of the reason could actually be more variability in cooperation, the fact that conventions exist. So like actually like we had some collaborations with Robert around like this idea of conventions, right? Like conventions end up being these arbitrary ways that you end up converging on doing a cooperative task. And you don't really like have that as much in competitions, right? Because competitions, if you're doing a zero-sum type of coordination, you are finding the most competitive way of responding to the person, and that reduces variability. But in cooperation, there might be a million different ways of cooperating, and those kind of introduce these different conventions or norms that you end up generating when you start cooperating. So then there's this question of, in cooperative tasks, which ones is it that has more variability? Which ones are they that have like more variation? And I think that kind of comes down to this question of convention dependence, which we had a paper on conventions at ICLR last year where we tried to formulate that a little bit. So Joanna was part of that paper too, who I think is in the audience. Yeah, so the idea of convention dependence is, if you pick cooperative tasks, there are some of them that require, like, that potentially can have more variability, more different ways of like getting at it, or you could have cooperative tasks that there are like maybe a few single ways of cooperating on them. So I think convention dependence could be really the thing that get to that variability and get to like when you would have more variability, and then you start needing to really like worry about your data and what type of data you're getting at. Does that kind of, I don't know, like address parts of this question? Should I continue? Okay, let me continue, and maybe we'll do like a continue, and then we can come back to this later. So yeah, so my answer to that is, yeah, it is absolutely true that cooperative settings, I think they're more variable. I think part of the reason is the existence of conventions. Convention dependence could be a way of formulating how much variability we have in cooperative data. And even in non-interactive, like if I'm trying to collect data for like a robot learning task, right? Like even if I'm trying to collect data for pushing an object, there's quite a bit of variability in that data. And that kind of connects it to what Robert was getting at too, like the type of variability that is present in the human data. So let me actually like get to that, because I think that has connections. So I think that's a very interesting insight, that we cannot, as humans, we cannot restrict our cognition, right? Like we kind of like see that in this robots data that you're looking at, right? Like when you look at human collecting robot data, there's a ton of pauses. And I'd imagine those pauses are, or you're paying attention to something else, or you're trying to like worry about like how to do it right, but there are like 5 other processes running in your head. So I think that is why we see these types of pauses. And I think in terms of what we can do functionally about that, we can either augment our data sets to also have those pauses when you're generating synthetic data. It can also has like these types of like weirdness that human data has, or maybe we can kind of clean our data sets and like not worry about it. So when I collect human data, if I can identify what are these task irrelevant things that people are doing, if I can identify those and filter those out, maybe that is the right way of going forward. But I think it is interesting to like think about task relevance. I think it can be difficult to identify what is task relevant and what is not task relevant. Like in the middle of like, I don't know, doing a task, like you end up itching your back, right? Like, how do I know that is not task relevant? That's again, like as a human, I have the context. I know that is not relevant about pushing, but like from a robot's perspective, it has no idea what is task relevant and what is not. So I think that is in general pretty interesting. And one other perspective that people take to address these types of things is that if I just throw more data, maybe it'll go away. So if I just make my data set large enough, so then I'll realize itching was not part of the task, maybe that will solve the problem. So I think that could also be like one way forward, just like making sure that our data sets are so large that these types of like variability, we start like ignoring them, and like the same way as a human realizing that itching was not part of the task, maybe we'll start realizing that. So that's kind of like those 2 points, variability in data. I think that's an interesting point. I think Dylan talked a little bit about learning from suboptimal agents, and yeah, I completely agree with that. So I agree with the fact that, yeah, we could learn more when you're learning from suboptimal agents. I added one more slide like later, like the iLead work, which is one way of trying to like get at learning from suboptimal agents. And we are seeing like similar results. Like if I have an agent who's good at hammering something, and if I have another agent who's good at screwing something, I can at the end of the day learn a policy that can be really good at like either one of these tasks. I think there are still like questions about how to go about this, especially if you have offline data sets that maybe don't have any labels of reward. In that work, we are making some restrictive assumptions about the human model, because like in this work, in that work, what is happening is we have suboptimal human data. We want to identify expertise and we want to identify a policy, and we don't have any rewards. So if you have adversarial human data, it's not going to work. It's just not going to work. So the assumption that we are making is that suboptimality is of a very particular type of suboptimality, which is you either do the optimal action or you are uniformly random picking any other suboptimal action. So that is how we are identifying what is optimal from the data set. That's kind of like a quick overview of like some restrictive assumptions that we are putting in there and how we are learning from suboptimal agents. I think in general, like one really needs to like work on that direction. I think it's a very exciting direction. And then the last point that Dylan made is kind of this question of, should cooperative data be collected or produced? And I think that's an interesting point, right? The fact that the parent is actually like, the parent wants to teach the person how to like take a bite. And that type of data where you're producing that type of data, that could potentially be pretty different from like, I don't know, random collected data. And that could be more informative, that can have explanations, that can have quite a bit of like more informative, useful type of data. I think we need to use both. I think it would be nice to have more like generated, produced type of data when we think about teaching, when you're thinking about these types of tasks, cooperative tasks. I think there was one other point that Dylan brought, which is when we are thinking about learning from play, should the goals be given? And actually the answer is no. So like the answer is, what I'm calling goal is just where an object has ended up after making contact. It might not be goal, like it might be like, I don't know, sub goal. It's just like what I'm calling goal is not really like a true goal that you might have for like a downstream task. But then the plan that you're learning is the plan that results in the object getting to that downstream like behavior. And you might end up like in some sense with a library of them, because you're now relying on this large offline play data, and you can potentially use these different Z's like online when you're going for like some other real like downstream goal. So in the test time, the goal is given, it's a goal condition policy. But in training, we are not really like calling things like real things, like we're just calling like where the object has ended up as a goal like frame. The previous work on learning from play kind of like didn't even do that, didn't segment the data in this particular way of object interactions. They just took a random 2-second window and they were like, oh, random 2-second window should have some information. And they kind of like treated it like that. And even then they started like, they had like some nice results, like even when they didn't treat the data like stringently as object interactions. Yeah. All right.
Okay, that's fantastic. So I think I'll now just kind of open it up to audience Q&A as well. And Dylan and Robert, please also feel free to come back on any of those points as well. There's obviously quite a lot there. So yeah, if people want to use the raise hand feature at the bottom under reactions of the Zoom button, at the Zoom bar rather, then you should be able to do that, and I'll call on people in turn. But I think, and Dylan, you've just unmuted, so if you want, I don't know.
I did. I think maybe I'll take advantage of the time when people find the raise hand button, and just say, I think maybe a clarification on the idea that on goals, and I think my point is the idea that what's interesting about moving objects around is changing the objects rather than changing the position of your hand or something like that. To me, I think that's that seems like perhaps one of the most useful types of extra information that you're bringing in there. And I think it would be really interesting to understand how that applies in more general settings, or how that relates to what you call an object, or how you like split the world up into different objects and having like a shared definition of that.
Yeah, that's an interesting point. Yeah, and like multi-object interactions start like being pretty interesting there too. Like when you push an object and it hits another object, like when do we like, how do we like think about like those types of like down the line effects? Yeah, current work is pretty simple, but I think it would be interesting to think about these more complicated settings. Yeah,
absolutely.
Nice. I think Robert, you just beat Vince to it. So if you want to.
Well, okay. I just had a brief kind of thoughts on, I thought, Dorsa, you put the point about the existence of multiple equilibria in cooperative tasks super well. And I think that really puts the finger on the difference. And I think that one thing, maybe going even a step further from that, is that we often talk about inductive biases like a single monolithic thing. But if you account for the fact that there's actually like extreme variability in the priors that different people bring into a task, right? Like there are people that like if you ask my grandma to like operate the tele robot, like it's going to be really different than if like a, you know, like an undergrad robotics student or something does it. And like, you know, my grandma will probably take a while to like figure out like how the knob works because they've never used like a controller like with the knob before, like hit the wrong buttons because they can't figure out. So I feel like the reason I mentioned that is just because when you're thinking about coordination, and everyone is adapting to everyone else, that's how you end up with these really like idiosyncratic solutions where like there really is like a different solution in every single different interaction, right? Like depending on the inductive biases of the person you're interacting with. So I think that yeah, I just really like that way of putting the difference between like a chess kind of game versus like a coordination game.
Yeah, that's a very good point. Yes, and then kind of like the fact that there's quite a bit of variability and personalization based on that. And like, what are all the diverse conventions that we can find? Like we really need to find the space of conventions. That can be a pretty difficult task. It is finding the space of potential Nash equilibria. That's a difficult task. Is a pretty interesting point. One other point that Robert, you mentioned is the fact that both agents are adapting, which we didn't really like talk about maybe that much in this talk. Like if you pair up like two learning agents, it's pretty like in the examples that I gave, it was either the robot is observing a fixed human, data coming from a fixed human, fixed distribution, or the human is observing the robot suboptimalities. Again, robot has a model, it's not changing, like it is changing that model, but it's not changing its learning algorithm. But in general, if you have like two learning agents that are paired up with each other, potentially with different learning rates, I think that can create all sorts of difficulties.
Yeah, I think you get out of distribution very quickly. Yeah.
Yeah.
Vince, if you wanted to jump on.
Thanks, Dorsa, for the talk. It was great. So I'm also fascinated by this idea that we may have very different solutions to the same problem. And it seems to me that in many cases, probably doesn't really matter, right? Like I don't really care if my robot, you know, isn't familiar with the idea of rotating first and it just rotates last, but it does everything I want it to do. I don't really care whether it has other solutions, right? And I imagine at some level, this is also the case with humans, that maybe like at some level, I ride a bike very differently from how you ride a bike. But that's totally fine. Like we both managed to ride a bike, even though like if somehow you could, you know, insert some of your actions into my bike riding, I would just fall over and I would have no idea how to deal with that. At some level, that seems okay, right? And yet at another level, it seems like in these kind of cooperation problems, and maybe especially, you know, like Peter Stone has this idea of ad hoc teamwork, right? Especially when you just have to like immediately play with another agent and it has to be right away. We don't have time for learning. Then it helps to have kind of a broad understanding of the different types of solutions that you might approach things with. Like maybe we see this in teaching as well. If you know, maybe certain kinds of math problems, like I figured out how to do them for myself, and that's fine. But I don't really know how to teach a class on it yet because people will have different solutions, and like I won't be able to anticipate them. Whereas on other kinds of problems, maybe I know how to do that better. So I'm trying to make some sense of like, you know, to what is the level at which we need to have a broad understanding of different approaches with which people or other agents might approach things with, right? It seems like it's helpful to have a broader understanding, but do we, and also as humans, do we ever learn that kind of directly? Or is it always just from interplay with other people, right? Like, I guess like riding a tandem bike, right? I don't know what helps you to ride a tandem bike well with other people. I presume like, you know, practicing riding tandem bikes with lots of people will, you know, help you with that, right? But is there some way I can ride my regular bike today, like try lots of different things? Would that actually help me ride a tandem bike with somebody else or not? I don't have the greatest sense of like, like it feels like something like this is relevant, but how much is a diversity of solutions to a single agent problem the thing that you need for immediate cooperation versus just learning in cooperative settings? I like that question. I have no answer to it. Yeah,
that's a very good question. I don't know if I have a good answer for it either, but it is a very good question. I think both. Okay, so when we think about riding a bike in general, riding a bike, like what does it take for us to ride a bike? I think one way of going about that, or one way, like you're looking at that problem, actually, one way of going about that is trying to identify what are the skills, like could we do skill discovery? What are the skills that go into riding a bike? And some of these skills are interactive skills. Like, for example, when you're like riding a bike, like some of it is really about the task, like about like just like figuring out like how to deal with the pedals, but some of it is about interaction, some of it is about coordination with other agents. So I think in general for these types of tasks, like there needs to be some level of skill discovery and potentially some level of modularity that separates what is it about the task that I need to do and what is it about coordination, like what are the skills that require coordination. And for the skills that are really just about the coordination, I think there we need to really have like this diversity if you want to have few shot like coordination with other agents. There, I think like this idea of diversity of conventions, diversity of ways of coordination can start like really like mattering. And we should like try to identify what are those different variable like data that we can get. And like maybe if you're creating a curriculum for a person to coordinate, maybe we should create curriculums that are more diverse and more variable. And this variability also has some connections to like creativity, right? Like what are the most like, I don't know, creative ways of like solving math problems? Like when you were talking about math problems, like in math curriculum generation, like I used to do some work on this like way back, on generation of curriculum for math. And like the idea is how do we come up with creative like math problems so they all don't look the same? And it's kind of the same problem. Like what is a diversity metric that we are trying to optimize? What are different ways of thinking about a problem? And I think that is needed. Again, it's two separate parts. Some about the task, but when we are thinking about interaction, especially like in these ad hoc teaming where you got to quickly coordinate, that diversity starts mattering. But if your goal, like my answer is really like this is task dependent. If your goal is to, at the end of the day, have a robot that can put a ring on a peg, that is what the robot wants to do. It's trying to learn from humans. It doesn't care when to rotate it. It just wants to like put a ring on a peg. And that is the thing that it wants to do in a data efficient way. Maybe for that goal, variability doesn't matter. I should actually give like very clean data so it learns like how to do the task right for the goal of the ring being on the peg. That is why like in that setting, I was like, oh, the robot maybe can be transparent about what it wants to do and like actually reduce variability in the data that it is getting, because the task is not coordination. The task is, I just want to achieve this. Like, and give me the cleanest data possible for me to achieve this. I don't want to see all possible ways of doing it. I just want to find one. So it kind of like goes back to this idea of, yeah, sometimes you want to find one solution in competitive settings. Again, sometimes you're finding that one solution that's the most competitive. But in these cooperations, like you start interacting with different types of agents. That is why maybe you should go for the more diverse, broad ways of going about things. So I don't know if that answered the question. Those are just some thoughts.
Thanks. I think Ram, I think if you can.
Yeah, hi. So hi, thanks for the talk, Dorsa. Thanks for answering my earlier question about the goals. So a question for either Dorsa or Dylan. Dylan, and I think I don't remember what Dorsa talked about this too, but Dylan raised the question of, is it possible that learning something competitive could be easier than learning something cooperative? So I was thinking, I mean, is it even possible to compare them? I mean, is there any objective metric that would compare the performance, because it's the performance on one game versus the performance on another game, which has to be different. So how would you objectively compare that?
I think that's a good question. I think I'm not sure. I'm not sure I have like a satisfying like the answer with a capital T. I mean, one possibility as a starting point might be looking at distance from a best response to your opponent. So if you compare your policy and you measure regret against a best response to your opponent's policy, for example, that would be a regret measure that I think could transfer from cooperative to competitive settings. I think, yeah, and maybe that captures the notion of some notion of like coordination with the other agent that generalizes from cooperative to competitive settings. But I think what I really mean from a harder standpoint is more of a subjective, like harder as an AI system designer or roboticist almost. So there's like comparing, like, does this robot do better in there? And then there's well, I as a researcher who's working on one competitive robotics task and another cooperative robotics task, which one do I find more difficult to get to a satisfying solution on? Which is maybe not, I mean, that's actually very much not an objective metric. But I think that's what I would point to in this case. Dorsa, I'm curious if you have anything else there.
Yeah, so I think Dylan kind of like already covered it. And yeah, like I think Dylan's points are great points. Yeah, the last point that he was making is really like the point that I think I was also like getting at, like what is harder is like what is harder from the perspective of kind of evaluating the down the line task, right? Like if I like do my algorithm and then have an overcooked agent that wants to collaborate with a person, is it able to collaborate? Can I evaluate and have like a high performance on that coordination task? That I would argue is quite a bit like harder with the same effort compared to like a competitive task. One other clarification. So like you had a question about in chat, I think, about the air hockey example. So I didn't clarify that air hockey example as much in the talk because I didn't want to go into it in detail, but that is not a competitive setting that we are looking at. We have a predefined policy for the partner that is state dependent and is dependent on what the other agent is doing. What exactly the partner is doing is it's pushing the puck. If it gets blocked, in the next time step, it's pushing the puck towards a different direction. So it's a kind of like a history dependent policy. It is not the most competitive thing. The most competitive thing to do in that setting is, it's actually kind of like rock, paper, scissors. The most competitive thing to do there is to play random. And if you were to play random, then you would basically, like, our algorithm would do the same as like basic reinforcement learning, because it wouldn't have like a better model of the person. Like I was trying to show more partner modeling, and that air hockey example, in general, I know air hockey is competitive, but that air hockey example that I was showing was not competitive. It was like a very fixed like partner model that existed there.
I understand. Thank you.
Right, I have my own questions. So yeah, I guess there's a few small ones. So maybe I'll just kind of like skip around and see how much time we have and who else puts their hands up. But I think the first one is a really good, it's a really basic kind of silly question almost, but you kind of mentioned these three objectives of better data, better algorithms, and then maybe also this idea of kind of flipping the question and trying to get humans to be less suboptimal and more helpful and so on. I'm curious from like this, like an overall perspective, where you think like the best angles are there. I mean, obviously all of these things are going to compensate for each other in some regards, but like if you had to kind of put your money on where the bottlenecks are, you know, is it really that actually we've got some great algorithms, we just don't have the data for this thing, or we have all this data and we just cannot make use of it because we don't have the algorithms? I mean, obviously it's not going to be either of those extremes, but I just wanted to kind of put I agree
that it's not going to be either one of the extremes. And I think in general, like any field, right, like I think it's going to be an iterative process. Right now, I think it is a data problem. Right now, I think, okay, so like if Sid's data is like rotating in different orders, if I just had lots of data of both types and an expressive model, like it would capture all of them. So it would capture everything. So I think right now there's quite a bit of effort in terms of collecting large data sets, that we could actually like tap into. And I think that is a good place to do things. But I think we'll saturate that. And once we saturate that, we'll go back to algorithms, and then we start thinking about like how to deal with algorithms. I do understand that there's quite a bit of push and pull between this question of data and models. I think as academics, we really like to work on algorithms, and like it's kind of unsatisfying to say, hey, like the answer is just, we just got to collect lots of data and maybe it'll work. Like I feel like that is in general like pretty unsatisfying. So I feel like as academics, we are going to like end up working on the algorithms side quite a bit. But today, I think the problem is we got to collect more data and then go back to, like, we got to collect more diverse, lots of data, then go back to like this question of how we should change like the algorithm.
Okay, this is perfect because this actually forms the nice little segue into my little follow-up question, which I wanted to ask anyway, and now have a great excuse to, which is what I guess, yeah, what sorts of data seem like the sorts of data that is really lacking right now. So, for instance, I'm going to mention like one example is there've been a bunch of people who've been floating ideas about what we actually need is we need a bunch more data about human preferences, and we need it to be really high quality, and we need this to be multimodal. And what we're going to do is we're going to then use this to kind of fine tune some of these big kind of monolithic kind of pre-trained models and so on that seem to be kind of, very effective at all these tasks. But what we actually just need is just better human data, and data about human preferences in particular over lots of different types of scenarios, et cetera, et cetera. And so, people are kind of proposing, well, let's, start an organization, let's start a group to actually go out and do this. And I'm curious if you think that there are obvious kind of categories. So one category might be actually, data like gathered from agents collaborating. You've got multiple agents moving around. You've not just got one human demonstrating a task. You've got data of two humans collaborating on a task. And then what we want to do from that is extract as much as possible about the idea of collaboration, the multiple different ways of collaborating, and then somehow make use of that. I'm curious if you have any thoughts about kind of obvious things where we just don't have as much data for stuff that we need.
Yeah, so I think that's a very good question. And I think in general, we should see what is the cause of these variabilities that we are seeing, like where the issue really exists. And that, like, based on that should inform like where we are collecting our data. I think it depends again on the task, right? Like if you're thinking about robot learning today, if I was talking about robot learning, I would say, okay, like that type of cooperation data is useful, but like I can't get the robot to push the object right now, or I can't like get the robot to like consistently open the door of the fridge in all different homes. So it would be wonderful to have like human data, but right now I just want all types of doors because that is like the thing that I have like not variability on. I just need to collect lots of data on that. And that is more kind of like on the offline training side of things. The type of data that you were talking about, I would say is more on the online adaptation side of things, which I definitely think is interesting. So I think they're kind of like two separate problems. Both of them are incredibly important. I think to address the online adaptation question of collecting more collaboration data, more interaction data that can help us with that online adaptation, we should first off have that offline pre-trained model. And I would argue that in robotics, we don't have that today yet. Well, in NLP, we do. So in robotics, like I think we need to also like have efforts of collecting large offline data sets. There's also this question of like model, like in terms of modeling, what can we do in terms of algorithms, what can we do? So there was quite a bit of an effort at Stanford around this idea of building large pre-trained foundation models. So the name had a lot of questions like afterwards. But basically, I think it is like in general a good idea. And we are trying to like push on that direction for robotics. So what would it look like to have a foundation model for robotics? What would it look like to have a pre-trained model? What is the type of data that is required for pre-training? But even beyond that, what is the objective that we need to have in pre-training for what downstream tasks? And all of these, I think, are interesting questions. So yeah, so my answer is really like for like you need data of both types, but the source of it should be like, where is my variability? And where is the problem? So that should guide like where the data comes from. I think one thing just to be wary of is just collecting data sets for the sake of collecting data sets without having any task in mind can be dangerous. Like there are a lot of driving data sets that were collected a little bit like, I don't know, 10 years ago that weren't really used as much. Part of the reason was it wasn't collecting the right things we should be looking at. It was just kind of like say, oh, we'll collect the data set and someone will use it. But I think it's a good idea before collecting large data sets to think about what is a downstream task that you're trying to do? Like, what does that adaptation look like before just finally collecting data sets? Yeah.
Yeah, definitely. Robert, I noticed you had a hand up a few times, but I wasn't sure if it was retracted multiple times, I think. So
yeah, I keep going back and forth because I'm looking at the time, and
I think go for it. I think we'll if you want to ask the last thing, then we'll say a last thing. Then
I think there's just I think that there is like just kind of going back to the original kind of topic of like what makes human data different. It's like there is this interesting tension where like we all know that the more variability you have in a data set, the better. Right? This is like the difference between like, I don't know, ImageNet and, like MNIST or whatever, you know, like there's just, it's like a really messy data set or whatever. And that was like really powerful because like the world is messy, and, you know, like that's the arguably like from like a cognitive science, neuroscience perspective, like what makes like what the problem that the human organism has to solve is like coping with the just like massive sources of variability in like the real world, right? Like our like in vision, it's the fact that literally like every time we move our head, we get like a completely different view, right? And it's like that's like arguably like the main problem that the human visual system has like developed to solve, is to like be able to cut through all of that variability and not be kind of like confused by something. And I feel like this is a well taken lesson, but it's harder in human cooperation because the data sets are so much more like expensive to scale up, right? Where it's like you can't just take like all of the images on the internet, like, you know. So I feel like this puts us into a position where then we get more conservative, and we're like, if I'm gonna pay like, you know, this much for a data set, I want it to be really good data, you know. And then you try to like take out all the sources of variability, but then you end up with like a brittle system that like can't cope with variability. So I feel like this is like the deep kind of like cost benefit trade-off, right? Of like, how can we scale up these data sets in ways that kind of like, yeah, have the right sources of variability that allow the agents to interact in the real world.
Yeah, no, I think it's, I agree.
Being cost, I don't know, cost prohibitive. Like, yeah, I don't, you know.
I agree that is the trade-off. Yeah, that is a trade-off that we deal with today. That's why a lot of algorithmic work are about, oh, look how my algorithm is so data efficient. It doesn't need all that data, my algorithm, which I think is good. Like, it's good to have like those robust algorithms that are data efficient. But like, again, like I think today it would be wonderful to have like more data, and like with like today's algorithms, see where that takes us, and really like then like go back to algorithms and like
yeah, because I think that this is the mixed effects thing again that I'm kind of like plugging on a little bit, which is the I dropped a paper in, well, I guess there's kind of this question of like, it's not just size that matters, and this was actually a big problem in psychology, where people were collecting these data sets where you'd have like a ton of observations for like a single participant or something, right? Like you'd have a single participant do a task like a lot, versus like having a lot of people do the task a little. And it turns out that like there's, with exactly the same data set size, like having variability across participants and are ideally across like items, which usually means like the task thing, like how you set up the task or whatever. It would be like what objects you put in the scene with the robot, or like how many different configurations you use. Like those axes like can cut by like orders of magnitude the performance of your model. So it's basically like if you don't have variability along those axes and explicitly model it, you just like it is equivalent to having like a much smaller data set, which I think is kind of an interesting, people think a lot about the overall size of the data set, like you report like the number of observations, but like thinking about like how many units is that coming from is like the effective size of your like variability in your data set. So I think that that's like a good perspective as well.
Good point, yeah.
I think yes, now is a good time to close, I think. So thanks once again, Dorsa, and as well to Dylan and Robert, and for everyone joining as well. Next week we have a talk from Gillian Hadfield, who is a trustee here at the foundation. And so yeah, hopefully you'll be able to join for that. And if not, we'll see you all in future. Thanks very much.